A very good afternoon to all of you. Now I am going to start the fifth unit, that is multiple dosage regimens. So here, for taking any type of dose for treating particular disease, we need to administer our dosage form at a particular dose levels. So if we will take this particular doses in multiple types, that means 2 or 3 or 4 times a day or 10 times in a week. So how could be the result? So that's why what are the importances we have to design a dosage form, how it would be. It is a very simple and very easiest unit. See, under multiple dosage regimens, you are going to read the contents of repetitive IV injection, that is by one compartment open model, repetitive extravascular dosing. Extravascular dosing is nothing but through oral dose. Okay, then this is also by on compartment open model. And the third one is multiple dose regimen for the drugs following two compartmental open models. You have three topics under this multiple dosage regimen. For knowing this multiple dosage regimen, how we will divide the repetitive doses for treating such kind of diseases when our drug should follow either one compartment or either by two compartmental open model. So, what is the importance of dosage regimen? It is defined as the manner in which a drug to be taken. This will be denoted by our dosage regimen name. Then, for certain analgesics are used to treat some pain, right? Then hypnotics, then antiemetics. These will be prevents vomiting. A single dose of the drug may provide an efficient treatment. So, for treating the analgesic property and hypnotics and emetics property, you can use the drugs in single doses. So the single dose is enough for producing effective pharmacological action. But only one thing, in these three diseases you may have longer duration of your illness. Okay, so if you have any analgesic, if you have any pain, okay, pain to your body, so it will take more time for treating, more time for cure. Okay, more time to cure such kind of this pain. Then for that, your single dose of the particular drug may treat it efficiently. Only thing is our duration of illness will take longer than the therapeutic effect produced by a single dose. What does it mean? The single dose will produces very efficiently short period of time. Your disease may get treated, but only one thing, our illness cannot be treated as that much faster. In such cases, you need to administer the drug on a repetitive base. So, up to prolonged periods of time. So, you need to take the repetitive administration of such drugs for effective treatment period. So, then you can relieve with that diseases. Then, what are multiple dosage regimens? See, when the duration of treatment of disease, when the duration of treatment of disease is smaller than the therapeutic activity, the single doses are given. So which type of diseases, which type of drugs we have seen? Analgesics and hypnotics and then antiemetics. So in that cases, we need to give single doses of a drug to produce an efficient pharmacological action. So in this case, your example is aspirin. Aspirin acts as a NSAID. That is nothing but non-steroidal anti-inflammatory drug. Aspirin is also called as aspirin is used in the treatment of fever, right? So for that reason, you need to take only single dose, then you can relieve from your disease, but 100% you can achieve only after taking a repetitive administration of your drug. Single dose you can relieve with the fever, but this fever can be temporarily relieved. Okay, so if you want to get permanent relief from this fever, you can take this aspirin in a multiple dosage regimen. That is nothing but repetitively you can administer with the drug. So you might have observed in your cases also, whenever you will get a fever, doctor will suggest you to take the drug up to 1 week or 10 days along with the antibiotics, right? So how the action of this drug will be? When you take the plot between time versus concentration, so the drug can efficiently produce its pharmacological effect in between the minimum effective concentration and the maximum tolerable concentration. That will be nothing but your therapeutic range. So here the duration of action, that is nothing but your Cmax of the drug, will be produced within the therapeutic range. In which cases, when you take the aspirin in the repetitive doses, in the multiple dosage regimen, you may achieve maximum plasma drug concentration levels which will attain at peak plasma concentration. That is nothing but Tmax. So you may achieve this Cmax at particular therapeutic ranges only. It should not be more than this MTC, and this below this MEC. Below this MEC, you have a sub-therapeutic level, and above this MTC, you have a toxic level. Can you remember this? You have a toxic level. So this, in this particular aspirin, this will be produces its pharmacological action, and it will be producing its maximum Cmax at therapeutic range only after taking this in the form of multiple dosage regimen. Then the next case is when the duration of treatment of disease is larger than the therapeutic effect of the drug. See, in case of antibiotics, here you are going to treat your disease in a long period of time. Along with the antibiotics, we have to treat our disease with a larger time period. So in that cases, multiple dosage regimen can be given in terms of by taking dosing intervals and area under the curve measurement. So we have other option to give or to treat the disease which is having larger than the therapeutic effect of the drug. Suppose you have to treat one disease, that is nothing but either cancer or you have any diabetes. For example, I am telling. So these diseases can be treated up to long periods of time. Okay, these cannot be treated under short period of treatment. So for that reason, the therapeutic effect of the drug is also more than. Then in such cases, how we need to calculate the particular drug which is suitable for treating these diseases, the particular drug, how we can calculate a multiple dosage regimen for that drug. How we can calculate? It is totally dependent upon the dosing intervals. At what time you are going to take your drug. Suppose you can take the drug at second hour, then after that you can take the drug at fourth hour, then 10th hour. These differences are nothing but the dosing intervals. Here the difference is 2 hours and here the difference is 6 hours. So with irrespective of the dosing interval differences, you can calculate the tau. Tau, this is called tau. You can write it like this. This is the tau, dosing intervals, and area under the curve. See here, when you plot the time versus concentration, you may get this zigzag mannered curve. This is indicating you the drug will exhibiting multiple dosage regimen. See here, this green color box indicating you the AUC, and here the difference of the dosing interval is 18, here it will be 24. So like that, here it is 12 and it is 18, 6 and 12, 0 and 6. Here the differences of the doses will be 6 hours. So for each and every 6 hours, you need to take AUC as a consideration. Then you can calculate, you have to add all these AUCs together and you have to find out the difference is obviously same, 6 hours. So then you got the multiple dosage regimen for particular antibiotics, so which is used to treat your disease longer period. For that reason, we need to administer our drug. In such cases, we need to administer our drug for multiple, that is nothing but repetitive dosage administration. So if you want to administer your drug in the form of single dose or in the form of repetitive dose, our aim should be the same. What is our aim? We need to achieve maximum plasma drug concentration levels. So only one thing is, we are considering our illness should be short period of time or else our illness should be long period of time. Based on the illness, we can select the drug what to be given. Then you have to make them in multiple dosage regimen, that is nothing but repetitive administration. Then you can calculate the dosage by using this equation. So what are the objectives of your dosage regimen? The overall objective of the dosage regimen design is to achieve a target drug concentration at the receptor site. The overall objective of the dosage regimen design is to achieve a target drug concentration at the receptor site. Wherever you want to target your disease, you need maximum drug concentration at your particular target of your disease. So the graph will be the same what I have shown previous slide. The main objectives for designing the multiple dosage regimen is nothing but to maintain MEC and MSC. If the drug will follows MEC and MSC, that is nothing but within the therapeutic range, it should be pharmacologically active. So the importance of these two parameters should be more and more while preparing the multiple dosage regimen or while adjusting the proper dosage regimen. What are those? Size of the dose of the drugs. Size of the dose of the drugs. Dosage size. This is nothing but dosage size of the drugs. Okay. Dosage size is nothing but your drug dose, 10 mg or 100 mg or micrograms or whatever it is. The frequency of administration is nothing but the time interval what we have to consider to take the next dose of the drug. The time interval between the doses. What we have observed in the previous slide, we got there only 6 hours of duration. So same like that. The frequency of drug administration is nothing but the time interval between the doses. So here, to make a multiple dosage regimen, you need to focus only on 2 points of the drugs. What are those? The dosage size of the dose and then the frequency of administration. If you calculate accordingly, you can get a multiple dosage regimen for particular drug. And one more important thing, here we are taking our drug in a repetitive manner. Okay, we are taking our drug in a repetitive manner. Repetitive manner. So in that cases, definitely we will get and drug accumulation. In which cases we will get this accumulation? Suppose if you want to take a drug at early morning 8 o'clock, 8 o'clock, then after this is the first dose, right? This is the first dose, and the second dose of the drug will be at 12 o'clock. Just for example I am saying, okay, this is the second dose, this is the second dose. So when you want to take this second dose, you have to clear out this whole first dose of the drug. Otherwise what is going to happen? Suppose your first dose should be 10 mg and the second dose is also 10 mg. Every time we used to take the same size dose of your drug. Okay. So in the first dose we have taken 10 mg. So at 8 o'clock, this is the first dose. And after 8 o'clock, at 12 o'clock, we need to take one more dose, that is also 10 mg, but this is called second dose. If you have you did not remove this total first dose, then you can take this dose, you have taken this dose, then what is going to happen here? There is a some some dose of the drug is there that will be remained in this first dose. Okay, without removing this first dose, if you take this second dose, what is going to happen? Your drug will get accumulated. Your drug will get accumulated. So without removal of your first dose, you cannot take your second dose. So how we can remove? So if you assume that we are a patients, right? So we have suffering with one disease. So first we can take your doctor will says to you, you have to maintain 6 hours of time interval. You can take the drug for every 6 hours. That is 3 times a day. That is for 3 times a day. So how the doctor will decides you to advise you or to take you the drug at least for 6 hours gap and then 3 times per day? It is totally based upon the elimination half-life of the drug. So we know how the drug will get eliminated and how the drug is having elimination half-life. It is totally dependent upon the elimination half-life. The doctor will suggestion you have to take this much time period. So within that elimination half-life time period, your first dose of the drug will get eliminated out. So no doubt you can take the second dose. Here there is a chance to prevent your drug accumulation. So if you are not at all prevented this drug accumulation, there is one more chance you may get some toxic effects. So that's why there is a need to remove your first dose of your drug. When the drug is administered at a fixed dose and a fixed dosing interval, accumulation occur because drug from previous dose has not been removed. Okay, accumulation of the drug will depends upon the dosing interval, the elimination half-life and the independent of the dose size. So how you can calculate this accumulation index? 1 by 1 minus e to the power of minus ket. 1 by 1 minus e to the power of minus ke tau. E to the power of Ke is nothing but your elimination rate constant. Ke. In some textbooks, they have written like e to the power of K. K is nothing but your Ke. So just remember that thing. Ke is elimination rate constant. Tau is nothing but dosing interval. Accumulation where the amount of the drug in the body build up with successive doses are administered. That's why I'm telling you, when you are administering the successive doses, and you may not sure that your previous dose cannot be removed from your body, then you may get accumulation. The drug will get accumulated in our body. So definitely you have to take the particular drugs at particular dosing intervals. And then you have one more concept that will be need to learn in this fifth unit, that is multiple dosage regimen. That is nothing but principle of superposition. Principle of superposition. An acceptable plasma concentration profile at steady state can be devised with the aid of pK parameters. Okay, since under third and second and sixth units, we know that after, when you take the plot between time versus plasma drug concentration, after certain time the plasma concentration will get steady state, right? So this steady state plasma drug concentration will help us to calculate the pK parameters. So the principle of superposition assumes that early doses of a drug do not affect the pK subsequent doses. So early doses means initial doses of your drug will not get affected your pharmacokinetics of the subsequent doses. So the drug is eliminated by your first order kinetics. After taking a single dose of the drug, the pK cannot be altered for multiple doses. Please remember this. If you want to take single dose for the drug or the multiple dose for the drug, multiple is nothing but repetitive administration, your PK will never altered. PK will never altered. Whatever the PK parameters you got for single dose administration, same PK parameters you got it for multiple also. Therefore, the blood levels after the second, third or fourth and so on will be superimposed. The blood level attained after the n minus 1th dose. So, what I am telling here, the principle of superimposition means when you take the drug in the form of single dose of administration or else by multiple dose of administration, the PK parameters will not be changed. Whatever the parameters you will get for single and for multiple, both are same. So that's why, therefore, the blood levels after second dose, third dose, fourth dose, etc. so on n minus 1th dose will remains the same. Then what it is indicating you? The dose of the particular drug will be overlaid or superimposed. Superimposed. The blood level will be attained after the n minus 1th dose. It will be superimposed. In addition, AUC 0 to infinity following administration of a single dose will equals to the AUC T1 and T2 during the steady state. This point is very important. So, for knowing the AUC from the zero time, from the initial time to the infinity time, we can take into consideration of T1, T2 plus AUC T2, T3 like that. So what it is telling, when you calculate this AUC 0 to infinity at the dosing interval of steady state, you may get the same values for 0 to infinity and that of T1 to T2. So that means the dosing intervals will be same. The repetitive doses will also be same. The predicted plasma drug concentration will be obtained by after each previous dose. So here we will predict some plasma drug concentration. That predicted plasma concentration which will be obtained by each previous dose, Because of the superimposition principle, it will be overlaid. It may be used to predict the concentration after multiple doses will be given at equal or unequal doses intervals. See what I told you previously. In some cases, your dosing intervals will be same. In some cases, your dosing intervals will be different. So, because of the principle of superimposition is nothing but you have to take the first dose, later on you are taking the second dose. Okay, so this first dose is there and the second dose is there. After removaling of this first dose, based on the elimination of your drug, you can take this second dose, but this second dose will be superimposed on the first dose, then this third dose will be superimposed on the second dose. So that's why the principle is called overlay method. This dose will be overlaid onto the other dose, the next dose or the previous dose, Okay, so then it may be used, these kinds of overlay or superposition principle can be used as to predict the plasma drug concentration after completion of your multiple doses. Suppose we have 4 multiple doses. Suppose we need to give 4 repetitive administrations for one drug. So, right. So in that cases, after fourth dose, it is going to complete its cycle. So after fourth dose, we will predict our plasma drug concentration of particular drug because of this superposition. See here. Here we have first previously we have 10 microgram plasma drug concentration. So after fourth dose, how much the drug will be available at particular plasma. Either it may be 10 microgram per ml or it may be reduced or it may be decreased after completing our nth doses. Then it is very easy to predict the drug concentration after multiple doses given at equal and unequal dosage interval. See ma'am, in this repetitive dose administration, each and every word is important. So you have 3 different kinds of compartment models here. This is repetitive IV injection by one compartment open model. Okay. So the maximum amount of the drug in the body, the maximum amount of the drug in the body which is following a single rapid IV injection. Here I am not talking about IV bolus or it may be IV infusion. Just I am talking about only IV injection is equal to the dose of the drug. For the dose of the drug which is following one compartment open model, it is eliminating out through first order kinetics. Then the equation will be after single rapid IV injection, your equation will be dB is equals to D0 into e to the power of minus kt. dB is the amount of drug remaining in the body. Here we are administering our drug in the repetitive manner. So for that reason, we need to calculate always the remaining amount of the drug available in the body. Okay, how much amount of the drug will be remained in our body, we need to calculate it. That is nothing but your D of B. Then B stands for body, D stands for drug remaining. Then here D is 0, total amount of the drug. Okay, total amount of the drug, and e to the power of minus kt. T is time, k is nothing but elimination rate constant. Next point, the time between the first dose and the next dose. For example, we will take number 1 and the number 2, first dose and the second dose. The dosing interval, that is 1 hour, right? 2 minus 1, that is 1 hour is our dosing interval. And then the amount of the drug which is remaining in the body after several hours. Here we are taking only first dose, second, next dose. Next dose means either it may be second, third, fourth, or etc. It can be determined with equation d of b is equals to d of 0 e to the power of minus k tau. Our equation is d of b is equals d of 0 e to the power of minus kt. Instead of writing time, we are taking here time intervals. That's why we are replacing the small t with tau, that is time interval. And then you have to calculate the fraction of the dose. So first we are taking time only, then we are considering time intervals because we are administering our drug in the repetitive manner, in the multiple manner. That's why we are considering dosing intervals. Then we have to calculate fraction of the dose which is remaining in the body, which will be related to the elimination rate constant, that is Ke, and the dosing intervals will be follows. See here, we are taking the differences between how much amount of the drug will be remaining in the body and how much amount of the drug we will take initially. For that reason, we have to calculate the fraction, that is d of b by d of 0. This is drug remaining in the body, and this is the total amount of the drug available in the body. This is equals to e to the power of minus k tau dosing interval. With any given dose, f depends on fraction of the dose remaining in the body will depends on elimination rate constant and tau. Here we have only two parameters, elimination rate constant and dosing interval. If tau is large, that is if dosing interval is large, f will be small because your dB is also small. See here, if your dosing interval is large, for example 10th hour and 20 hour, here we have 10 hours difference. This is our dosing interval which will be large. Then your f will be small. Why? Because here the drug which is remaining in our body is small. Why the drug remaining in the body is small here? See, because of this much duration of time, this much dosing duration of time period, our drug will be eliminated out 100%. Okay, there is no chance to get 0.1% also, because our drug is having this many duration of time, that is nothing but time interval. So if our duration of time interval is large, then our fraction of dose remaining in the body is small, because the amount of the body available the drug available in the body is also small. It is very simple, it is a logically point. Okay, and then so this is one method to calculate your drug which is following one compartment open model with this repetitive injections. That method, this method I told you from Venkateshwarlu VVR textbook. Okay, in this textbook this is mentioned in this pattern. And if you want to write more and more regarding this repetitive injections through one compartment open model, and that you need to calculate it from plasma drug concentration based on the superimposition principle, you can take this derivation part. It is very simple. Once you focus it only for 6 to 7 minutes, I'll finish up this class. Let us consider the drug was repeatedly injected. The drug is repeatedly injected through a IV dose. That is nothing but X naught with the dosing interval of T hours. The maximum concentration of the drug available in the plasma. So before going to derive this equation, you just remember the basic equation, basic relationship. C0 is equals to X0 by Vd. Next equation is C is equals to C0 into e to the power of minus Kt. Here we are calculating repetitive drug remaining in our body. For that reason, we have to take consideration into initial administered dose and the next dose. So for that reason, here we are taking initial administration and the next dose C1 or C2 or Cn. For that here we are taking only C. C is equals to C0 into e to the power of minus Kt. K is elimination rate constant. T is time. The concentration of drug in the plasma at the end of the first dosing interval. At the end of the first dosing interval. First dose in the sense it will be C1 0. 0 means initial. Your drug concentration will be 0 and you are taking the concentration of the drug as a first dose. So that C10. See here. It will be given by C1 tau. So we are taking first dose now. For that reason there is no proper time interval. So for that C1 tau is equals C10 into e to the power of minus K tau. We are always taking our dosing intervals into consideration. But here we are considering only the first dose interval. That is the plasma concentration at the end of the first dosing interval. C1 tau, C10 into e to the power of minus Kt. At 0 time concentration, how it will be? At 0 time concentration of drug in the plasma following second dose. Here it is following second dose. How it will be? The second dose C2 tau which is equals. How we will get a second dose? We have to add the first dose. Then we have to add the initial dose. Then we will get second dose. Initial dose we have to add and the first dose we have to add. Then we will get the second dose. But we have a equation that C1 tau is equals C10 into e to the power of minus Kt. Then you can replace that. C2 tau is equals C10 e to the power of minus K tau. It is very simple. See, C2 tau. Then plus C10 is as usual with that above equation. So therefore, C2 tau is equals T10 e to the power of minus Kt plus C10. This is what I have written. Then instead of writing e to the power of minus Kt, we can write it as capital R. Capital R. When you remove this exponential form with this repetitive IV injections, you can write this e to the power of minus Kt with this capital R. C10 capital R plus C10. The drug concentration in the plasma at the end of second dosing interval is C2 tau, C20 e to the power of minus Kt. See here. Then we have C1R, C10R. So e to the power of minus Kt is nothing but R. So here we are calculating the plasma drug concentration at the end of second dosing interval. Second dosing interval is nothing but C2 tau which is equals. If you want to calculate second dosing intervals, we need initial second dosing drug concentration with that of minus k tau. So instead of writing k tau, you can write R. So C20, we have an equation. C20, we have an equation C10R plus C10. Okay, sorry ma, here you have to write 0. This is not tau. This is C10. Okay, see, this is first dosing interval. This is clear. And then this is second dosing in this is second dose C2 tau. For calculating second dose, we need first dosing interval and we need initial dosing. But we have an equation C1 tau is equals this. Then we will replace instead of C1 tau, you have to replace this one. Therefore, C20 C20 is equals C1 into e to the power of minus KT plus C10. Okay. So then your equations will be like this. And this above procedure can be used for finding out zero time concentration, that is maximum plasma drug concentration, and the drug concentration at the end of dosing interval. End of dosing interval is nothing but nth dose. For each dose, you need to calculate in the same manner. See here. Here we are calculating C30, C3, third dose initial. So for that we need C2 tau and C10. C2 tau and C10. So we have C2 tau equation. This is what. Then C10 is as it is. So we will get this equation from the previous equation. Then you have to write instead of this e to the power of minus k tau is R. So same thing I have written here. So then this is the initial drug concentration and then this is the at the proper time intervals you will get C30 into R. R is nothing but e to the power of minus k tau. Then this C10R plus C10R plus C10. See here C20R plus C10. So when you want to write the continuation from the previous equations, you will get this. It is very simple. Okay. So therefore, the plasma concentration at the beginning and end of nth dosing interval, it can be given by, see here, it is for beginning dose, it is for ending dose. If it is a beginning, you need to write C10 plus C10R plus C10R square. So your here your R value e to the power of minus k tau value is getting double here in the beginning stage. Then at the ending stage, here you need to take only C10R1, C10R2, C10R3 like that. So for this beginning equation and ending equation, these two are useful for calculating the plasma drug concentrations at proper dosing intervals. Since R is always smaller than 1, Rn becomes smaller than as n increases. It is very simple. Once you learn it, if you have any doubts, I will tell you. Okay.